Hi guys, the problem we're going to be looking at today involves projectile motion in 2 dimensions. So this is going to be sort of a natural extension of some of the problems we dealt with in previous videos where we had motion in 1 dimension. So the equations of motions that we used will still be the same tools. We're still going to use those in 2 dimensions, but now we have an x and a y direction to deal with. And so the big thing that we need to keep in mind here is that those equations of motion will be applied separately to the x and to the y direction. So what that means is that quantities like velocity and acceleration in the x direction will not play a role in determining the velocity and the acceleration in the y direction. So that might seem kind of natural, but if we think about an example, that can be a little bit counterintuitive. So if we think of the example where we shoot a bullet straight in the x direction, and then we also drop a second bullet at the same time, at the same height, we can see from what we just said that the motion in the x and the y are sort of separate. That would mean that these bullets should both land at the ground at the same time. And so the reasoning there is that the motion in the x direction is certainly different for these bullets. One of them has a large initial velocity to the right, say, and then one of them is dropped. So the x direction motion is totally different, but the y motion is actually the same. All of the quantities in the y direction, so the initial velocity of both bullets is 0, the position is the same, we drop them from the same height, and then also the acceleration is gravity for both of them. So all of the quantities in the y direction are the same, so that means that the motion in the y direction must be exactly the same. So therefore, as they both fall down in the y direction, they should both reach the ground at the same time. And that's what happens in the real world. So without air resistance, that's what you would see. So that's good, and we'll see how that plays out in a more complicated problem here. So the problem statement for today reads as follows. 2 tanks are engaged in a training exercise on level ground. The first tank fires a projectile with a muzzle speed of 250 meters per second at 10 degrees above the horizontal, while advancing towards the second tank with a speed of 15 meters per second relative to ground. The second tank is retreating at 35 meters per second relative to ground, but is then hit by the projectile. Ignore air resistance and assume that the projectile hits at the same height it was fired from. Find the distance between the tanks when A, the round was first fired, and B, at the time of impact. Okay, so there's a lot going on in that problem. So let's draw out what's going on very explicitly in, I'm going to split this up into 2 diagrams. So our first diagram is what I will call initial, and then our second one will be final. And so our first diagram is going to be the situation where the projectile has just been shot from tank 1, and then the final will be where both of those tanks have moved a little bit and the projectile is just hitting tank 2. So for this first one, let's draw the ground, and then of course we can label our coordinate system. So I will label x equals 0 this point here, and then similarly we can label y is equal to 0. So this corner is going to be x equals 0, y equals 0. So now I'm going to draw the tanks. I'll draw tank 1 in green. And so tank 1 starts at x equals 0, y equals 0, and then it's going to move to the right with a velocity of v1. And then similarly, tank 2 will be somewhere over here, and it will be moving to the right with a velocity of v2. And then there is another object here, of course, and that would be the projectile itself. And so this projectile is going to have some initial velocity, which I will call vi here. And then this is going to be shot at some angle theta with respect to the ground. And so then it's important to note that this projectile really is existing at y equals 0. So all of this sort of has some extension in space, but we'll assume all of this is happening at the position x equals 0, y equals 0. So this is our initial scenario, and then the one thing I'm going to do is extend this motion. So I'll draw a dotted line, and that's to say we know once this projectile leaves tank 1, it's going to undergo this sort of projectile motion, and it'll eventually land over here on where tank 2 will be in some amount of time. So this is sort of projecting in time forwards, so this is where it will land eventually. And what I'm going to do now is sort of draw down here that scenario where it has just landed. So similarly down here we can draw our ground, and then we can draw our coordinate x equals 0 will be this position. Again, y is equal to 0 will be here. So this corner is still x equals 0, y equals 0. So now tank 1 will have moved to the right some amount, and it still has some velocity. They tell us these tanks have some constant velocity. And then tank 2 now will have moved to the right, and it will now be directly under where we set up here that this projectile was going to land, which is to say that the projectile at this final position when it lands on tank 2 will be right here. So we'll have just hit tank 2. So what we can also do now is sort of draw out. So we know tank 2, basically, I'm going to draw in these dotted lines. This is where tank 2 was. So it, in this time, has moved over this much distance. And this is where tank 1 was. Tank 1 started at 0, 0. So these are our two scenarios. This is initial. This is final. So the one last thing we want to draw on these diagrams is a couple of the distances that we have and that we can solve for. And that'll just make things easier down the line. So one thing we know is that in the end we really want to solve for the initial distance and the final distance between the two tanks. So these won't necessarily be the same, but we'll draw on the diagram where those will be positioned, which is to say this is what I'm going to call the initial, which is the separation between tank 1 and tank 2 just as the projectile is fired. And then, of course, down here we will have, let's call this the final. So that'll be the separation between tank 1 and tank 2 as the projectile hits. And then one other thing we can label is we know the distance that the projectile will travel in its motion will be what we are going to call the range. So that starts here from 0, and then it's going to end up over here where we said this is sort of where the projectile will land. So this is the range, and this is important because the range is something we can solve for from 2D equations of motion. So we'll take the equations of motion, solve them in the x and the y, and we can get to this range. So that's something to keep in mind with these problems. Is something like a range for projectile motion is something you should be able to solve for. And so in this case, we also have one other thing I'm going to write on here, which is that the distance that tank 2 moves from initial to final, I'll just call that d2. And then similarly, down here, I'm going to label this d1. So these are slightly extra, but they'll come in handy, which is just to say the distance that tank 2 moves before it gets hit is d2. And then down here, I'm labeling the distance that tank 1 moves in that amount of time is going to be d1. Okay, so now we have our diagram drawn out. Everything is labeled. It's been very laborious, but we've gotten to this scenario where we have all of our ranges labeled and all of our distances labeled. So now what we want to do is look at the motion of each object. So what I'm going to start with is the object of each tank, and the reason is that the object of these tanks is actually quite simple, and that is because there's no accelerations on the tanks. So really the only thing we need to know about each of these tanks is tank 1, distance 1 is going to be equal to v1t. So that's just to say the velocity of tank 1 is distance over time. I'm just multiplying the time over. And then similarly, the distance that tank 2 travels at any given time will be v2 times t. So this just gives us an idea of the distance that each tank is traveling with respect to time. So we'll leave this alone for now, but this really tells us all we need to know about each of the tanks. And so we're now going to focus on the projectile motion part. So we're going to be looking at the motion of this projectile here. And so for this, I'm going to draw a table, and I'm going to label each of these columns x and y. So that's to say we're going to look at the motion of the projectile, and we're going to separately look at the x motion of the projectile and then the y motion of the projectile. And so for this, we want to fill out our knowns and unknowns. So one thing we can say is that x starts at, the projectile itself, starts at x naught is equal to 0. And then another thing we can say is it ends up at a distance of r. And again, that's from the labeling that we did before. We don't know what this r is, but I'll leave this as just the x final will be equal to whatever the range is. So we'll leave that as unknown for now. And so then now we want to solve for the initial velocity in the x. And so we need to make one big point about this initial velocity. And that is to say that this initial velocity must be taken with respect to ground. And so if this v naught x is with respect to ground, what we want to start by doing, of course, is splitting up this vi vector into its components. So this here will be vix, and this will be viy. So that's I. So that's to say that we can split up this velocity vector, which is at an angle, into its x component and its y component. But this vix does not equal to the initial velocity with respect to ground. What this vix tells us is the initial velocity of this projectile with respect to the tank that it's fired from. But the tank that it's fired from has an initial velocity with respect to ground itself. So what we have to do for this total initial velocity with respect to ground is we have to add these two vectors in the x direction, which is to say we have to add v1 to Vix. And so from trigonometry, we're given this angle theta, by the way. So from trigonometry, you should be able to see that this Vix should be equal to Vi times cosine of theta. So this is our full, this is the full term for V naught x, which is to say it's not just the component of the initial velocity it's fired from. We also have to add to that the tank itself has a velocity. And so if you're having trouble thinking about that, think about maybe a moving sidewalk on an airport. And so if you're standing on that moving sidewalk, you'll be moving with some velocity with respect to the ground. And if you, for instance, maybe walk next to that moving sidewalk and you see someone to the right of you walking with the same walking speed, it'll look like they're moving faster than you. And in fact, they will be moving faster than you with respect to the ground. So you really have to add those two velocities. In that instance, you would have to add the velocity the person is moving on the sidewalk with the velocity that the sidewalk is moving to the ground. So that's what this is. Okay, so now we have our initial velocity. Our final velocity in the x we're not concerned with, but we don't know it, so I'll put that as a question mark. And then we know our acceleration in the x is going to be equal to 0. And so this is an important point, which is that for most of these problems, the acceleration in the x will be equal to 0. We usually don't have anything accelerating an object in the x direction, because once this projectile is fired, that would amount to something pushing this forward in the x direction further and further. So it needs to be speeding it up more and more as this moves along. And we see there's no rocket or anything attached to this that's going to shoot this forward with an increasing speed, so our acceleration must be 0 in the x. So the other thing we don't know, of course, now is time. So time is our other unknown. Now we can do the same thing for the y. So I'll do that right here briefly, which is to say y naught is going to be equal to 0, y final also 0, and that's just saying the projectile starts and also ends here. So our final is going to be when it is come back to the ground. It's going to end at a position of 0. So that will give us our full motion when it's come back down to the ground. So then our v naught y now will actually be simple enough. That will just be equal to VIY. That's to say there's no extra velocity pushing it upwards more in the y direction, so we can just take this component of the initial velocity. So that will just be VI sine theta. And then again, VFY we don't know. We're not going to be concerned with it, but for completeness sake, we'll write it right there. And our acceleration in the y direction, as usually is the case, will be negative gravity. So up is positive, so this is really minus g. And then similarly, we don't know our time. So we don't know the time that it takes for it to rise and fall back down to the ground. So now we have our full table, and it's all drawn out. So now we need to decide what we want to do with all of this information. It's a lot of information, and it's really almost too much information. So one thing that we need to focus on in these 2D motion problems is seeing that at this step, the important thing to solve for is often the time. So usually we'll want to solve for the time, and the reason is the time sort of ties the x and the y directions together. That's like the glue that holds the x and the y motion together. If you can solve for the amount of time it takes for this projectile to reach back to the ground, we can then plug that time into this x column and then solve for the distance it will travel in the x direction in that time. So that's what we're going to want to do. So if we do that, we should be able to use an equation of motion here, and we have quite a lot of information. So it turns out if you use the first equation of motion that you've been given, which is to say x minus x naught is equal to v naught x t plus 1/2 ax t squared. If you plug in your values for this, actually we'll plug these values in for y. So this is true both in the x direction and in the y direction. So we have both of these equations, and these will both be useful. So we're actually going to look at the second equation, which is the y one. And so if we plug in our values for y, we see y minus y naught is 0. V naught y, I'm going to leave all of this in variable form. So we have this times t, and then we have minus 1/2 g t squared. So I've just plugged in minus g for ay. And so now we have an equation which can now give us time. So we know all of these other variables, so I'll let you follow along in detail on the solutions, but you should get that time is equal to 2vi sine theta over g if you solve. So again, I'm going to leave this in variable form. In the end, you can plug everything in if you want, but this right here is really what is important. So that's to say we've now just found the amount of time it takes for this projectile to reach back down to the ground. So what we can now do is plug that into this x column and solve for the range, so the distance in the x. And so again, you can follow along in the solutions, but what you should eventually get, you'll use this same equation, this x equation right here. You should then eventually get that x equals r, again x final here, is equal to what we defined as the range, and that should be equal to vi cosine theta plus v1, and then all of this is going to be times 2vi sine theta over g. Okay, so now we have used our time, we plugged it into the x, and we got a solution for the range. So at this point, we're almost done with our problem. We're not quite done. But now that we spent so much time at the beginning setting up these diagrams, the next step is actually much easier than it could have been. And so that's to say we have a range and we want, for instance, di and df. But if we look at our diagram, range and di are related, and if we can solve for d2, we actually can figure out our answer very quickly. So that's to say, if we want to solve for di, we would have to take di is going to be equal to our radius minus d2. And we see that here again. Radius minus d2 should give us di. And so one thing we now note, again, d2 we solve for at the very beginning. It's going to be v2 times t. Our t is here. So we really have all of the steps we need now, and it's just going to be an amount to plugging it in. So again, check your solutions if you want the specifics, but you should then get that your di is equal to 2,000 meters. So that's our first answer. And then our second one we can solve for is going to be df. And so then in the same reasoning, we see df is down here. So if we want df, we can take r minus d1, and that'll give us df. So r minus d1. And then if you solve for that in the same way, you should get 2180 meters. So now these are our final answers. So we now have our initial separation and our final separation. So let's quickly review what we just did to get to this answer. We first drew our diagram, being sure to label everything very clearly. Then we noted that the tank's motion would be a simple constant velocity motion, whereas the projectile motion requires the equations of motion. So we applied these equations separately for the motion of the projectile in the x and the motion of the projectile in the y. We used that to find the range, and then we noted that the time quantity was what tied those two motions together. Then we referred back to the diagram and we saw how that range was related to each of the separation distances that we wanted, and we directly solved for those. Alright, I hope this video was helpful to you, and I hope it showed you that with a little bit of persistence and drawing a careful diagram, we can split up these two-dimensional problems into some one-dimensional problems, and then we can solve them that way. And so please leave your comments on any of these videos in the video tab on TED. There should be a survey for your comments on there underneath all of these videos. And other than that, thanks for watching.